we should know what Newton's first law is, the 28-word definition that was given to us. But what exactly does that tell us? Or what exactly does that mean? Well, an object in motion will stay in motion at a constant velocity. So what does that mean? Why? What does all of those words mean? Well, if we were in outer space where there is little to no outside forces acting on this ball, then if I were to throw this ball, it would just keep on going forever at the same velocity and forever in the same direction and speed, etc. Because there is no other forces to stop it from doing what it is doing. But now, obviously, we're here on Earth, so if I try rolling this ball, it will eventually come to a stop. The reason why this is because other forces are acting upon it that are unbalanced, such as the Earth's gravity, which is pulling it downwards, and then friction, which is making it not slide as smoothly on the surface, and then of course wind resistance, which is very, very small, but I mean there still is wind resistance from the wind pushing against it. And that is actually part of Newton's third law, which I'll get to later. But if we were in outer space, like I said, if there is no other, like theoretically speaking, if there is no other forces acting on it, it'll just keep going in the same direction forever and ever. Now if there were also no forces acting on it in space, and it was staying still, it would remain like that, unless an unbalanced force would act on it. An unbalanced force is a force that results in acceleration. So obviously, if an unbalanced force acts on this little ball, obviously it's gonna move, and so it will not be remaining at a constant still state. And then of course, we know the flip side of this, and this also works on Earth. I mean, if I put this ball here, there are no forces acting upon it, so therefore it's just going to stay there forever until some other unbalanced force, such as my hand hitting it, acts upon it, and then it will no longer remain at rest. Now, Newton's second law is one famous equation: force equals mass times acceleration. So what does that tell us exactly? Well, we know that force is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. So what that tells us is that if a certain object weighs, let's say that this weighs 1 kilogram or something like that, and we want to move it at a acceleration of 2 meters per second squared, well then we would have to exert 2 newtons on this object to get it to move at that, if it weighed that much, and if we wanted it to move at that acceleration. Now, if we wanted it to move faster or have a greater acceleration, then therefore the force will change. So let's say we wanted to move this at 10 meters per second squared. Say we wanted to move this 1 kilogram cube, Rubik's cube, 10 meters per second squared. Well then, it'd be 10 newtons. So obviously, since we are making it move faster, we have to exert greater force on it, and that is shown in the formula. Or it also works the other way. Say that we wanted to move this 0.1 kilogram cube at 10 meters per second squared. Well then, it'd only be 1 newton because it has a less mass than before. So therefore, the force drops because the variables dropped. So just like any other formula, if you change one thing, the other thing will have to change if you want the outcome to be the same. And then of course, if something changes, then the outcome will change. So Newton's third law tells us for every force applied, there is an equal and opposite force applied. So, for instance, if I try to push this ordinary Rubik's Cube, if I try to push it across the surface, I can do that, but I can feel the resistance of it putting the force right back onto me. It has the more mass that it has, and the more I'm accelerating it, will result in a higher force that is needed to be applied. This goes back to Newton's second law. And so therefore, if I'm making a heavier object move faster, I will feel more force being applied back onto me. Now, if, for instance, we say that Rubik's Cube was actually a wall of some sort, and then say that Rubik's Cube was an immovable object. So that means that it would have to apply X amount of force to stop me from pushing it if it doesn't move. So therefore, it is exerting a greater force than I am exerting with my finger, so therefore it is not moving. Now obviously, I can move it very easily, but we're just talking in theoretical purposes.